Okay, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, in Section 2 of Module 5, we're going to talk about deadlock detection. So now we know that in the multi-programming environment, when multiple processes are running concurrently, sharing the common data, deadlock may happen. Deadlock may happen. So now how can we, first detect any deadlock, or then later on we can actually prevent the deadlock to be happening. So in this section 5.2, we're going to introduce an algorithm that is used to detect whether deadlock has happened or not. Okay, now this algorithm is called graph reduction algorithm. Okay, now what is the graph reduction algorithm? So remember that we use the graph to display the current resource allocation for the processes. Okay, now the graph reduction algorithm is going to do the following two steps and repeat the following two steps. So the algorithm looks like this. It's pretty simple. It's kind of recursive. It's just doing the loop. So now we're going to repeat until no unblocked process remains in the graph. Okay. Now the step 1, select an unblocked process P. Then remove the P and including all request and allocation edges connected to the P. So we can remove the P and also remove the arrows that the process P connect pointing to, and also the arrows that point to the process P. So that's the graph reduction algorithm. Now, what's the purpose for this? Okay, now before we talk about the purpose for this algorithm, we first talk about a definition called completely reducible. Okay, so a resource allocation graph is completely reducible if at the termination of the graph reduction algorithm, all processes have been deleted. Okay, so now in order to detect whether the current the resource allocation is in a deadlock or not, we can actually apply the graph reduction algorithm. Okay, so then once we apply the graph reduction algorithm, at the termination of the graph reduction algorithm, so we continue to repeat the the reduction algorithm, and then we find out at the very end all the process has been deleted, then that graph, resource allocation graph, is called completely reducible. Okay, now what's the purpose for that definition? So now let's take a look at two theorems. Okay, now theorem number 1, a state S is deadlock state. Okay, so when you see a graph allocation graph, a resource allocation graph, and then at the current state is a deadlock state, if and only if the resource graph of S is not completely reducible. So that means for the current graph, if we apply the graph reduction algorithm and we eventually cannot completely delete all the processes, so that graph is that state S is a deadlock state. So the state of this current graph is deadlock state. Okay. So this is important because eventually we're going to use this theorem 1 to decide whether the state of the current graph is, deadlocked or not. Okay. Now theorem 2, all reduction sequence of a given resource allocation graph lead to the same final graph. So this is important because, this means, so I can actually apply the graph reduction algorithm, and I delete process 1 first. Okay, if process 1 is unblocked, then I delete process 1 first. And then process 2 is not unblocked, then I delete process 2 first. Okay, now until I delete all the unblocked processes. Okay, and then either it's completely deleted, all the processes are deleted, or there's actually some kind of remaining processes are all blocked. Or another one, just apply the graph reduction algorithm, and that person may actually delete the process in different order than I do. So, he or she may delete process 2 first, which is unblocked, and then delete process 1. So it's using different order. Now, theorem 2 basically says it doesn't matter which order you're going to delete the unblocked processes. Eventually, all the reduction sequence of a given resource allocation graph leads to the same graph. So eventually, the final graph is going to be the same. Okay, so I use my own sequence, and the other person use the other sequence to delete the processes, and eventually the final graph is going to be the same. So that means this is going to give you some kind of idea that okay, it doesn't matter. Just apply the graph reduction algorithm. Whatever the order of deletion is, it's fine. Eventually, it's going to lead to the same, final graph. So that means if you actually lead to a deadlock because not all the process has been deleted. If you actually follow this sequence, you lead to deadlock. That means it's deadlock. Okay, so the original graph is in deadlock state. Okay, it doesn't matter which order you delete. Okay. Now let's take a look at an example. Okay, so let's take a look at an example. Now here's a graph, a resource allocation graph. Now we try to use the graph reduction algorithm to decide whether the current graph is in the deadlock state or not. Okay, now let's follow these the procedures for the graph reduction algorithm. So based on the algorithm, we need to actually remove the processes that are unblocked. Now let's take a look at this. Which processes are unblocked? So we know that both, for P1 is already holding 1 unit of resource 2, but P1 is requesting for 1 unit of resource 1, right? And P4 is requesting for 1 unit of resource 1. Now, because resource 1 is available, so we can say that both P1 and P4 are not blocked. So they are unblocked. So based on the algorithm, so we should delete these unblocked processes. Let's say I first delete this. Okay, let's say I'm going to delete the process 1. And also I can delete the process 4, right? Both of process 1 and process 4 are unblocked. And also I should delete all the edges that directly pointing to the process 1 and the resource that process 1 pointed to. Okay, so I'm going to also delete the edges. Okay, so let's see after this. Now, what's the next graph looks like? The reduced, graph. So we still have R1, okay, and so we still have process 2 and the process 3, right? We still have process 5 and the process 6. Now, in the first graph, process 2, process 3, 5, process 5, and the process 6, they are all blocked because they are requesting for resource 2 or 3, but all the units for resource 2 and 3 are, not available. So their requests going to be blocked. They cannot continue with that. So all these 4 processes are blocked. So I put a red color which represent, the blocked processes. So after I actually delete P1, P4, and all the edges connected to P1 and P4, then the reduced graph is going to be like this. R2, R3, so still here, still requesting, still request, still request, still requesting, and that one's still there. This is still requested, and this, P3 is still continue, still actually holding 1 unit of R1, but that's it, right? So both P1 and P4 are gone. Now, let's actually, okay, so let's just color it. And then we just find out that once actually I removed P1 and P4, then 1 unit of R2 is available, right? So in that case, so the request from P2 or P5 were actually are not blocked, right? So they can actually finally get the resources. So that means P2 and P5 are not blocked anymore. It used to be blocked, but it's not blocked anymore. And let's see, P3 is still blocked, right? P3 actually are requesting for 2 units of R2, but there's only 1 unit of R2 available. So P3 is still blocked, and the P6 is still blocked because P6 is requesting for 1 unit of R3, which is still not available. So that's the revised that graph. Now, as we mentioned in the algorithm, we're going to repeat this reduction process. So now we're going to remove this 2, right? Okay, and also we're going to remove the edges. So now let's just jump to the next one. So now we have R1, we have R2, and we have R3. So now P1, P4, P2, P5, they're all gone. There's only P3 and P6. You have to apologize me. I have to twist a little bit. Okay, so now P3 is holding resource 3, right? Let me actually delete that one. And P6 is still requesting for R3. Okay. Now P3 is still requesting for the 2 units of R2, and P6 is still holding 1 of the resource 2. Is that all right? Yes, I think that's probably the case. Okay, now let's see. Let's color it. So we still have, oh, sorry, I put a different color. Okay. Now what's the color for P3 and the P6? Are they still red? That means, which means that they're blocked. Now, it looks like yeah, P3 is requested for 2 units of R2. So there's no way you can satisfy this, right? P3 is currently still holding 1 unit of R3. So P3 cannot get all the resources. It's still blocked. And what about P6? P6 is holding 1 resource of R2, 1 unit of R2, and still request for R3, but R3 is not available. Blocked. Okay. So looks like now this is the final graph. Right? So the final graph is deadlocked because you cannot reduce the graph any further. You cannot delete R3 or P3 and P6. Okay. So that means this original resource allocation graph is in a deadlock state. So now we know that for a resource allocation graph, we can always use the graph reduction algorithm to test whether it is in the deadlock state or not. So for any resource allocation graph, we can always test whether it's in the deadlock state or not, okay, whenever we want to do so. Now, however, it would be more efficient if that testing is done on continuous basis. Okay, so the continuous deadlock detection proceeds as follows. So here's how we're going to do the continuous testing. So if a current operation is a request for a resource, okay, so if the current operation just says one of the process just complete the job and free up the resources, then we don't have to do this continuous deadlock detection because this is going to make the situation better. But now, if the current operation is a request for resource, okay, so then the requesting process becomes blocked, okay, in the current graph, the resource allocation graph. Then we have to execute the graph reduction algorithm until one of these 2 cases actually happen. Okay. Either P is removed from the graph, then we stop the graph reduction algorithm, or no unblocked process remains in the graph, then we stop. Let's see how we're going to use this, approach to do the continuous testing. Okay, so now here's the example on how to use the continuous deadlock detection, during the operations. So now this is a graph, resource allocation graph. Now this graph is not in the deadlock state. So currently it's not in the deadlock state. Why? You can easily check this by using the graph reduction algorithm, right? So the graph reduction algorithm tells us to eliminate all the unblocked processes, okay, and also the edges connected to these processes. So P1 and P6 are not, blocked. So I can eliminate P1 and P6 and also the edges. Okay. So after I've done this, so then both units for R1 are available, right? So that means P4 can get the resource R1 because both actually units for resource R1 are available. So P4 can grab it. Now P4 is unblocked. So then I can eliminate P4, right? And also the edges. In the meantime, R3 is available, right? After P6 is deleted. So then P3 can actually, grab the resource of R3. So now P3 is unblocked. So I can eliminate P3. So if I can continue to do this. So eventually I'm gonna be able to eliminate all the processes. So this graph is, reducible. So it's not in the deadlock state. Okay, that's good. Now let's check. Now what happens? Now suppose the next operation gonna be, so when gonna be like a P1 try to make a request for resource R2. So that's the next operation. So P1 is making a request for more resources. Now P1 is currently unblocked, but after P1 makes such a request for R2, R2 is not available, right? There are 2 units for R2, but both units are currently held by other processes. So when P1 makes such a request, P1 is blocked. Okay, now that gonna triggers the continuous deadlock detection because now we have to, perform the graph reduction algorithm to make sure that these new requests will not lead to a deadlock state. How can we do this? Okay, now let's see. Remember, P1 is not available. P1 is blocked now. So now 6 processes are blocked. Only P6 is unblocked. So if we use the graph reduction algorithm, so we can eliminate P6, right? And also the edge. So after I do this, now what happens? I have a P1, I have a P2, P3, and P4, P5. Now P6 is eliminated. R1, R2, and R3. Okay, so this is assigned to R1. R1 is making a request for R2, and R2 is a request for R2, and this is assigned to R4, and the 2 requests to R1, and here. Okay. Now, once P6 and then all the edges to P6 are removed, now R3 is available, right? So now we can see that this is eliminated. So then we can actually change this to the arrow. So now P3 is available, right? After this, P3 is available. Okay. Now, what about P2? P2 is still blocked. P1 is blocked. P4 is blocked. P5 is blocked. But P3 is available. Now that's good. So then I can eliminate P3, right? I can eliminate P3. So let's see. Let's eliminate P3. Okay, and the edges. So what's the next situation? So I have a P1, P2, no P3. I have a R1, R2, R3, and the P4, and the P5. Okay, so P2 is requesting for R2, and one of the unit for R2 is assigned to P4, and the P5, oh, I think a P5 is, also make a request here. Oh, sorry, that's wrong. P5 is actually here. Actually, P5 is also, in this case, P5 is also available. I should say that. Okay. P5 is also available. So in that case, P5 should be eliminated as well. Okay. Okay, both P3 and P5 are available because they're both request for the resource of R3. It doesn't matter which one acquires the resource first, but once P3 acquired first, P3 gonna complete and make the P4, P5 unblocked, or either way, the other way around. So it should be okay. So okay. Okay, so let's see. Now, this one is still request for R1, and this one is still assigned to P1, and P1 is still request for R2, and then all the edges related to P3 and P5 are eliminated. Okay, now yes, that's the final. Okay, so now we see that P1 is still blocked. No, I think one of the resource for R2 is available now. So yeah, so both of these. Okay, so yeah, both P1 and P2 are available. And for P4, it's held one resource of R2, but still request for resource of R1. R1, there's only one available, one unit available. So P4 is still blocked. Okay. So now in that case, we can next eliminate the P1, right? And also P2. So now we can stop. We can stop the actually graph reduction algorithm by one of the conditions, because one of the condition is satisfied. So we're going to perform the graph reduction algorithm until the process P1 that make the request is deleted. Okay, so that means, what does that mean? So that means, so when you perform the graph reduction algorithm, you can eventually eliminate P1 that originally make the request. So that means by adding additional request from P1, this is not going to be make the new graph in the deadlock state. So we can accept that request. Okay. So that's basically what the continuous deadlock detection gonna do. Okay. Now, in a special case that when all the resource has only one unit, okay, so then the deadlock detection gonna be much easier. Okay, we have used a special approach to actually detect whether a graph is in the deadlock state or not. Okay, so in this slide, we're going to talk about the deadlock detection with single unit resources. So suppose all the units have single unit. There's no actually multiple units. Okay, now with a single unit resource R, only a single allocation edge can exist. So in that case, if I have, say, this is a resource, and because there's only one unit, and then if a process requests for it, there's only one edge, right? There's no multiple edge, okay? And also, when a resource is allocated to a process, and there's only one edge, okay? So in that case, now for the purpose of deadlock detection, to simplify the graph, the resource can be removed. So instead of like doing, say, okay, so P1 is requesting for resource R1 and R1 is currently held by P2. Instead of doing this, we can actually simplify the graph to P1 actually is relay on P2. So the resource can be removed. You can remove that resource and from the graph along with the allocation edge. Okay, so now we have a process P1 directly pointing to process P2. Okay, now so for any resource allocation graph and with all the resource with a single unit resources, we can eliminate all the resources that we can actually simplify the graph by, directly connecting the processes. Okay, now this is called wait for graph. So a wait for graph is a resource allocation graph containing only processes. Okay, where each process can have multiple incoming resource allocation edges, but only one outgoing resource request edge. Okay. Now, here's the theorem. Okay. So that's basically it's a proven statement. So using the wait for graph, a circle in the wait for graph is a necessary and sufficient condition for deadlock. So now to detect the deadlock, it's relatively easy. We just need to check the wait for graph to see whether there's a circle, okay, in the graph. Now, this is a necessary and a sufficient condition for deadlock. Okay, now let's actually take a look at the example. Okay, now let's take a look at this, resource allocation graph. Now, remember that, keep that in mind that in this, resource allocation graph, all the resources have only one unit. Okay, only one unit. So in that case, let's check whether this is the graph, okay, which is in the deadlock state or not. We want to test whether, check whether this graph is in deadlock state or not. Now we can, of course, use the graph reduction algorithm, right? That graph reduction algorithm always works. Okay. However, because all the resources have only one unit, we can use the wait for graph. Okay. Now let's see how can we use the wait for graph. Okay. So the key part for the waitful graph is to eliminate the resource directly. So let's see. We have a P1, P2, P3, P1, P2, P3, P4, P5, P6. Okay. Now, we only try to find out the dependency between the processes. Okay. For example, process 1 is currently request for resource 1, but it's not available because process 4 is currently held the resource 1, right? Because there's only one unit. So that means process 1 is dependent on process 4. Okay. So to do this, we can actually think about this. We can try to eliminate that resource. Okay. Once I eliminate the resources, and then you can directly see there's a pointer from process 1 to process 4. Okay. So process 1 is relay on process 4. Okay. And also, you will find out once this one is eliminated, the other edge is impacted. So process 5 is also request for R1, which is currently held by P4. So process 5 is also relay on process 4, right? So we're going to draw another edge from P5 to P4. Okay. Is there anything else? I think that's it. Now, next one we want to see is if I eliminate the resource 2. So now P2 is relay on P5, right? P2 relay on P5. Who else relay on P5? P3 is request for P2, R2, right? So R2 is held by P5. So P5 is, P2 is relay on P5. P3 is also relay on P5. Okay. Now what else? P6 also request for R2. So P6 is also relay on P5. Okay. So there's 3 edge, pointing to R2. So that means they were now directly pointed to P5. Okay. Now let's eliminate the last resource R3. R3, there's one, P2 is currently held R3. So P4 is the only process that requests for R3. Okay. So now let's do this. So that means P4 is relay on P2, right? Because P4 is going this way and going that way. Okay, so relay on P2. Okay, I think that's pretty much it. So that's the wait for graph. So wait for graph basically carries the same information as the resource allocation graph by eliminating the resources. But that graph is much simpler. Now, is there a deadlock in this graph? You just need to check whether there's a circle. Okay. Now, yes, you can see that P4 is relay on P2, and P2 is relay on P5, and P5 is relay on P4. So now we have this kind of circle. So there's no way you can break the circle. Okay. So there's a circle. So there's a deadlock. Okay. So that's the wait for graph. Now it's pretty simple. You just need to check whether there's a circle, right? Instead of doing the graph reduction algorithm, you can just check the graph itself, the wait for graph. Thank you.